I'll get our panel started. Are chiplets actually necessary?
If you look at the types of devices that are being used for AI, they are large. You know, they take a lot of parallelism, they take a lot of engines running in parallel, a lot of data moving between them. To try to build a monolithic device, it's become very cost prohibitive, and being able to build it out of smaller entities, building blocks, and scale it that way is that's a first order improvement over trying to build a single monolithic device. Even though the gentlemen to my left do build a single monolithic device, but it's also very expensive.
Well, I heard a couple of interesting things in a session earlier today that I haven't heard before. And one of the things I saw is that we're going from a 1x on a PCB, to like a 10x on a chiplet, an SoC, but then it goes to 100x very quickly when you go from 2D to 3.5D. I didn't realize that. Now we're talking about a new word I have learned was called the SysMore instead of Moore's electronics. The SysMore, I think that's a great word because it allows us to think in terms of how we can get more performance and capability out of the systems we build.
I think you have to do a pro and con analysis in every case. It is not a one-size-fits-all answer. I mean, we are at the Chiplet Summit, of course, and so we love chiplets. But there is a chiplet tax also. And of course, there's a power performance penalty, but it is also complicated in terms of business, in terms of like test. So there are many nuances to this. And I'd love to hear what NVIDIA has to say, because they have chosen not to go along that path for some time, at least publicly. So it is important, but necessary is dependent on the use case.
Yes, since Nick and Rohit both brought me, so chiplets are extremely important, and even though we have monolithic product right now, but we are reticle limited. So we are going in the direction to have chiplets. We of course are part of UCIE as well, just for that reason. So we, as I said, reticle limit is causing us to look at all sort of options for chiplets, whether it's advanced packaging with 3D or 2.5D, so all those options are there. And that's the only way to grow given Moore's law is slowing down, or you can say that. That's the only option to move forward.
And given the nature of this panel discussion is supposed to be about how chiplets can accelerate generative AI. So I'd like to make the point, it was actually recognized in the last panel section, that all of these computes that are trying to get to generative AI, they're all using high bandwidth memory. And high bandwidth memory is a chiplet technology. So it's absolutely necessary now. And if you look at, say, and what we want from a chiplet ecosystem, the definition would be, you've got chips with different functionality, and they're differentiated, and they come from different companies, and you use advanced packaging technology to integrate and have products that you can't do. And HBM has enabled that ecosystem for the first time. If you look at an AMD or you look at an Intel compute engine, whether it's a GPU or an SoC, they're all making the chiplets for themselves except for the HBM, because they communicate with an I/O chip, not directly to the DRAM. The DRAM stacked on top of the I/O chip. So we already have the necessary that you need a chiplet technology established for today's generative AI. And in the future, there's a couple big trends that are going to make this even more important to have a chiplet technology for all the companies. One is that as we go to HBM4, that I/O chip, which is now on a DRAM process, is going to be on a logic process. And once you put it on a logic process, then where you do the integration between today's compute and today's memory is up for grabs and for innovation. The other thing is, if you look at it this way, an HBM die is just like a core compute die. That's all it does. And the peripheral stuff is all controlled by a separate I/O chip, which I said is now going to be logic, and now can be developed with different IP partition between the SoC or the computing, just call it XP, in the memory. And the last trend that's an important one that to consider, advanced packaging also enables the possibility to get rid of the PHY on both the compute side and the memory side. And what I mean by that is you just simply say, wherever the memory controller is, just have it talk directly to the global IOs inside the DRAM. You don't need to go through any PHY to do that. And so you lower your power, you save on latency, and you have the potential to have even a higher speed bit on this.
Just chime in here from a slightly different angle. Paul mentioned innovation, and I come from an innovation angle because I lead the venture group at Lam Research. To answer your question, are chiplets needed? I would say from if venture investment is any indicator, the answer is yes. Over the last 10 years, there have been over 100 investment deals that were completed just for chiplet-related technologies, and that's based on a quick search I did. I'm sure it's off. It's probably much more than that. 100 deals and about $2 billion of venture investment. So, $15 to $20 million per deal, and the ecosystem is just so creative when you have the ability to assemble building blocks that are specialized in different functions. You can think of all the permutations that results in. Whether these investments are going to pan out is another question, but it's an indication of the creativity. The other aspect is, again, I'm coming from the capacity point of view in the semiconductor industry, providing the tools. When we can start using depreciated legacy nodes to now repurpose and build valuable components and chips that then get used in bigger systems, that's another benefit to the industry. So, we're a very creative industry, whether it's innovation or reusing, capacity, repurposing capacity.
Well, we have a bunch of wires. We also have UCIE as a standard. Is there space or requirement for additional standards? And does something like UCIE meet the needs for something like generative AI?
I'm part of the UCIE board representing NVIDIA, and we did talk about it as a board and also in the technical task force. So UCIE provides the interface. It does not go inside the chiplet architecture. So UCIE, in terms of the bandwidth, in terms of the power and power per millimeter square, is very well suited for generative AI. And what generative AI specifically means here is that you have the compute portion and the data portion, and both are equally important because data is really moving. So with the large language models, you have billions of parameters, and compute, your goal is to make the compute busy all the time because that's the expensive component, and keep the data ready from the memory. So the way partitioning works in this chiplet is that you have the compute, and then you have the memory and some of the caching architecture at a higher level. And UCIe fits in very well, whether it's 2.5D or 3D technology to feed in the data coming from the memory and into the compute to better utilize the full compute advantages.
I can add one comment to that. I think, I agree with Durgesh that we have standards already, right? So my feeling on this is that let's not have more standards, more fragmentation, right? We kind of have to coalesce against that. And then we have to define what is the challenge we are really facing in terms of making like chiplet economy or whatever you want to call it, because that still has not happened, right? And I contend, this may be controversial, but I contend that we need to do more in figuring out what are the problems preventing that, like form factor, like other flows, boot flows, reset flows, etc., and standardize on more and more of those things rather than bringing up another interconnect standard.
Yeah, I see how much work has gone into PCIe over the the decades to get it to the maturity level that it is today. I mean, UCIE is at, 1.1. I think that the points you raised about resets and clocking and, system, partitioning, all those will have to be tackled with UCIE. I think UCIE right now is just a foundation, but we need to build those system aspects of it out. And I think that's going to take more time.
Talking with customers, I can understand that they always want standard IP. If that's what the customer wants because he wants the comfort of standardization and it's going to be on the chip anyhow, yeah, we'll support it. But one of the questions I have about UCIE is you can't read and write to memory at the same time. And all these things are read intensive. So you're dedicating half of your I/O pins for writes. So it's not bi-directional. So it seems like if you were trying to design a good memory interface for a chiplet, that's not the one you would come up with. And then I've also thought, working with customers on 3D solutions. And of course, UCIE is a 2D solution. And if I'm doing a 3D solution, I would never, ever make it unidirectional or take half of the I/Os and have them dedicated to a write instead of a read. So I don't know how much people have really thought this through or how applicable UCIE is for a pervasive chiplet interface for the memory subsystem.
Yeah, memory is important, especially the bidirectional same pin. But 3D is work in progress right now, so you will see the 3D related changes coming in the new spec whenever we publish it, but that is work in progress for sure. On the memory side, I think it will come after that, which we'll work on.
Okay. Along the lines of manufacturing, what are some of the challenges that everybody's encountering now? And do you think these things are going to be continuing, or are they something that after a year or two we're going to find smooth sailing?
I think the advanced packaging is obviously a challenging technology. We have, as I said, the HBM that is based on silicon interpolers or EMIB or whatever the case would be. But making systems that are repairable or reconfigurable to get around faults, I think, is going to be a key thing here. We've put extra bits into the UCIE or the bow to take care of the missing connections that obviously mucks around. But I think as these densities get higher and higher, especially with 3D stacking, I think we're going to need much more repairable, reconfigurable systems to get around faults to be able to make these things high yield.
Moving along in terms of manufacturing, one of the things that has always been cropping up is where you get into manufacturing. How important is it to have US-based fab and chiplet manufacturing capabilities?
Answer that or give my opinion. I believe it's extremely important because once you have chiplets, you are taking chiplets from various sources, and when you integrate them, there's a security problem. Who's responsible for the chiplet security? Who's providing for any RMAs and returns which are happening, or even testing and manufacturing? So those are, and even tying to the previous question, so the overall manufacturing will take some time to settle down, and to do that, to have a proper secure system, we have to make sure all the providers, whether they're chiplet providers, whether they're packaging providers, substrate providers, they're all coming together and assembling the chip and find one person or one company or one entity which will be responsible for the solution, given their various components.
Actually, you raise an interesting point about chiplets and things like counterfeit chiplets and having the ability to actually have the chiplets self-authenticate. So the same mechanisms you do today to sign code and private public keys, I think we're going to need to have some sort of a mechanism by you can trace the history of the chiplet and authenticate it before it gets put into a package.
From the manufacturing side, we certainly we have seen technologies where it's possible to add like a small secure ID tag onto a chip, and there's a lot of questions about that. But certain applications like military may require knowing the provenance of chips. So there's certainly innovations that are working towards that.
Going back to the supply chain question, high bandwidth memory is obviously in high demand right now. the use of chiplets is probably going to drive that significantly more. Are we gonna have enough chips or high bandwidth chiplets available?
No, look at the guy from the
No pressure.
Well, as everyone knows, there's back-end shortages, but it's good news in that the demand is so high for these type of products. But yeah, for memory solutions like that, I mean, they're constrained, right? I mean, you want higher density right now. If you're using high bandwidth memory, then you're stacking higher. We started with 4, we're heading to 16, but you know, you started to thin these things down to 40 microns. I mean, just as a frame of reference, a piece of paper is about 100 microns. So there's a limit there. And so if you need more density, it's like then you're gonna need more HBM put in onto a package. So there has to be, in my opinion, some innovations on interconnect technology to be able to achieve having more of that memory. And other than that, just in terms of going faster, you only have a couple choices. Is just try to design the silicon to go faster in the IOs, and that consumes even more power, or you make them wider. And we're already at 1K, width for HBM3. So there's constraints on what you can do with these type of memory solutions. So again, we're seeing kind of like the limits of stacking to get more memory. There has to be innovations in interconnect packaging, or perhaps optical interconnects in the future, so you can get more of this memory that way.
Well, I'm very glad you mentioned that, because I was going to bring up that, again, I'm coming to this panel with an objective to look a couple of years out and sort of support different technologies that can unlock various bottlenecks. And I think the interconnect bottleneck is a big one. Everybody knows about the memory wall issue. So definitely we are more than happy to provide more capacity for HBM and for chips, but pretty soon we're going to need to figure out how to speed up the interconnect process. So one area that I'm very interested in is high bandwidth interconnects, either through optical methods or other techniques. So that's definitely a really interesting area, for the next few years.
I'm just going to make one comment about the memory wall. So I was working at Intel in the late 90s when I was first recruited to work on memory. And the way I was recruited was I was told that there was this memory wall. It's getting worse and something needs to be done. But we keep finding solutions at different levels to get around these problems. So see, I'm optimistic.
Okay. And as a systems vendor, we will support both of you in finding solutions for this problem. I think the models are getting more and more complicated, and with the new models coming up, it's going to become worse. So your memory wall is getting higher and higher, Paul.
And something's got to be done about it.
Oh,
I guess another question along those lines, especially if we're talking something like IoT, is what are the advantages that chiplets are going to be providing in that space? Is it bandwidth? Is it just the ability to put things on a single package? Because we do have multi-chip packages already.
My take is really the customization. What I mean by that is that you cannot have a one size fits all. So we have general purpose computer, of course, CPUs have evolved. I have worked at Intel for a very long time. But things are changing. So if we look at BERT and GPT, both are transformer-based model, but BERT uses the encoder blocks, whereas GPT uses the decoder ring kind of architecture. So even you can see the same, where they came from the same architecture, but they are doing it differently. So to address the requirements to growing compute, we will see customizations. We will see that we will place some chiplet for something specific usages like accelerators and some for different usages. And chiplets are a solution to help us provide those solutions So to solve that problem of increasing compute, and we can address it, so there's not just one solution which is trying to address everything. So that's where I feel the customization is the key for the applications and usages we are seeing as a chiplet as a solution for that.